This next section, we'll call it 5.7b, is about trig substitution. And some people find this a little challenging. Actually, it's probably because they don't realize some very basic facts. First off, if anywhere in the integrand there is a square root sign with a quadratic underneath, that is, a square, second degree polynomial expression, you're going to use trig substitution. Now, some of these problems can get very involved because there are either coefficients in front of the x squared term or there's a middle term, an x. We are going to stay away from those higher end problems and just focus on some basic ones where we either have the difference between two squares or the sum of two squares. And in the box I've summarized the three forms that can come up. If we have a number squared less x squared, it's going to call for us to replace x with a times the sine of theta. You might say, why at this point? Well, I think you'll see the beauty of it or the trickery of it in a moment when we do some examples. If, on the other hand, it's the sum of two squares, and of course the order doesn't matter, it's going to suggest that we take the x and we replace it with a times the tangent of theta. And again, that will become clear as we work through an example. And finally, the other combination is, what if we have x squared minus some number squared? Well, that's going to call for us to take the x out and put in its place a times the secant of theta. Now, in these problems that follow, these example problems, I've taken the time to work them out or write them out in advance because they are a little long, and I'm going to talk through what's on the screen and make a note here or there or underline here or there. I would suggest to you that as you're looking at the video, you stop it from time to time and just kind of take in the steps and the process that you'll find on the screen, and then either advance it to go past my discussion if it all makes sense, or continue it to see what I've got to say. So let's take a look at the first example, and the first one will correspond to this first form. We'll look at a problem that has a radical sign with an a squared minus x squared underneath. So here is the issue. We've got a quadratic under a radical sign. It's of that form, a squared minus x squared. And what I've done off to the side here is I've said, well, let's consider the fact that in this problem, a squared is 16, so therefore a is 4. If I'm going to use this, I'm going to say that I'm going to allow x to equal 4 sine theta, and I see already in this problem a dx, so I know I'm going to have to take a derivative, and the derivative of 4 sine is 4 cosine. So this is, of course, all done off to the side, and I'm going to bring it back to the problem, and I'm going to say, okay, I had an x squared, so I'm going to take x squared out, and I'm going to put in its place 16 sine squared theta. And under the radical sign, I'm going to do it again. I'm going to take the x squared out, and I'm going to put in 16 x squared theta. And then I'm going to replace the dx with 4 cosine d theta. Now I know that looks just terrible, but be patient. You'll see that good things are going to happen. So now it's just a question of reducing where we can, bringing things together. And the first thing I noticed that under the radical sign is that both terms have a 16. And so I could take the 16, factor it out of the two terms, and the square root of 16 is 4. So I could drag that out front, leaving behind under the radical the 1 minus sine squared. That's all I've done in this first step. Now I'm noticing that, geez, I've got these factors of 4, so they can go away. And this 16, well, I'll drag it out front and write a 1/16 up front. In addition to that, I note that 1 minus sine squared is a cosine squared. So now, what have I got? Well, I can take the square root of cosine squared, that's just a cosine. And now I begin to notice that, geez, the cosines knock each other out. And I've got 1 over 16 times the integral of 1 over sine squared. Now, 1 over sine squared is the same thing as cosecant squared. And although this integral does not show up much, the integral of cosecant squared is related to the integral of secant squared. The integral of secant is tangent. Secant squared is tangent. Well, the integral of cosecant squared is negative cotangent. So there it is. And you might be thinking that we're done, and we almost are, except that, do you recall the original problem was not written in theta, but rather the original problem was written in the variable x? So we need to think about our substitute, and it all relates back to this line right here where we said take the x out and allow it to equal 4 sine theta. So think about the fact that x equals 4 sine theta. Doesn't that suggest that sine isolated is equal to 4 over x? And you know, sine is opposite over hypotenuse, right? So if SOHCAHTOA, remember that? So if that's true, we can draw sort of a generic triangle here, a generic right triangle, and take our angle theta on the lower left and say, you know, if the opposite is x, then the hypotenuse must be 4. So just based on that drawing, this mystery side, this third side, the base if you will, we know by Pythagoras that the mystery side squared plus the x squared has to equal 16. Therefore, our unknown side, our base squared, is 16 minus x squared. And this mystery, this base, it has to equal the square root of 16 minus x squared. Now, why are we interested in all of that? Well, remember our answer from above here, our answer from above, which I copied down here. Based on this situation, given that cotangent is adjacent over opposite, cotangent is adjacent over opposite, I can come to my problem here and say, well, let's take cotangent out. Cotangent is our mystery side, our solved side here, our adjacent over our opposite, which is x, and I'll place that in for my cotangent. And now my final answer written in x is negative radical 16 minus x squared over 16x plus c. Again, a rather lengthy process, a lengthy problem, but this one is pretty standard. So maybe stop the video, maybe backtrack a little bit, pause it, take a look at what I've done, see if it all makes sense. Let's go on now to a second example. And this second example has the sum of two squares under a radical sign. Remember, trig substitution, any quadratic under a radical. Well, this is the form where we said take the x out and put in its place a tangent theta. So again, coming over here, we realize that a in this case is 2. Based on the fact that we want to let x equal a tan theta. In this particular case, it'll be 2 tan theta. And looking ahead, knowing that I have a dx, I know the derivative of tangent is sec squared. So 2 tan theta, the derivative will be 2 sec squared theta d theta. So now I'm going to take my original problem and I'm going to begin maybe writing 1 over and the square root of 4 plus, and then I'm going to take the x squared out and I'm going to put in its place 2 tan theta squared, which works out to 4 tan squared theta. And then I'm going to multiply that by the dx, and the dx, we solve that out. It's 2 sec squared theta d theta. Now, this problem looks far worse than the original, but let's start manipulating and working with what we've got. First of all, do you see the common factor in the two terms under the radical sign? The 4 can be factored out from the 2, and the square root is 4 of 4 is 2. So I'm going to bring that up front, and I'm going to leave behind 1 plus tan squared. Up top, I'm going to move this 2 sec squared theta to the numerator here. And I'm going to notice that, geez, the 2's can go away. And then I might remember my Pythagorean identities, that 1 plus tan squared is sec squared. So I'm going to take 1 plus tan squared out and put in its place secant squared. And then I get a little bit excited because the square root of something squared, of course, is just secant. And then the sec squared over sec reduces to sec d theta. Now, at this point, you could simply go to your table and look up the integral of secant. But I've got an opportunity here to do one of my integration techniques that is not formally talked about anywhere in the textbook, but I think you could appreciate it. Consider this problem, and the problem is the integral of secant. Notice how it can be done. You can take at this point and bring into the problem a factor of 1. Now this factor of 1 is done with some thought or consideration. We're going to multiply secant by something over itself, a factor of 1, and that factor is going to be sec plus tan over itself. Notice what happens if I take the secant and multiply it by each term in the numerator. Won't I get sec squared plus sec tan? Now, again, this looks pretty awful compared to the original problem, but consider the simple substitution sec plus tan. If I take sec plus tan out and let that be u, won't the derivative be sec squared, the derivative of secant is sec tan, and the derivative of tangent is secant squared. Isn't that the derivative of that u? And isn't that what our numerator is? Our numerator is in fact sec squared plus sec tan. So I'm going to take that whole numerator and my du out. That whole thing, I'm going to take it away, and I'm going to write a du in its place. And that leaves 1 over u left for replacing the denominator. Sec plus tan will replace that with the u. Then that's the natural log of the absolute value of u. And now if I bring back my substitution, isn't that the natural log of the absolute value of sec plus tan plus c? Again, you might just want to look in a table, but I couldn't help myself to bring up how or where that comes from in the table. You know, the table, somebody's done all the work for you, right? We enjoy their work. There's an indication of where it comes from. So, our original problem, back at the beginning, it was written in x, it wasn't written in theta. Right now we have a solution that's written in theta. So let's consider our original substitution where we said, well, take x out and let it equal 2 tan theta. Doesn't that suggest the tangent is equal to x over 2? Putting together this generic triangle, this generic right triangle, if the lower left is our angle theta, then opposite over adjacent is tangent. It means that this side, the opposite side is x and the adjacent side is 2. And then Pythagoras tells us, well, the hypotenuse must be the sum of the squares of these two sides. X squared plus 4 under a radical sign will be the hypotenuse. So we'll bring that back now to our problem, and our problem says the natural log of the absolute value of secant. Well, secant, of course, is the reciprocal of cosine, and cosine is our adjacent side over hypotenuse, right? So secant is the reciprocal of that. So that's where we come up with this radical x squared plus 4 over 2. Tangent's a whole lot easier, right? We identified tangent earlier as simply being x over 2, so let's put that in for tangent. And once again, I looked at the back and said, what's the answer to this problem? They did something that I didn't expect, or had it in a form I didn't expect. But consider what happens if we factor out the 1/2. If we factor out the 1/2 from the two terms under the absolute value sign. Well, don't we get something like what I have in this next line here? We can also drop the absolute value sign, because think about it. If I square anything, it becomes positive. If I took the square root of x squared, it would be a positive x. So it already overcomes the possibility of x being a negative number, because the net of those two would be 0. But think about under the radical sign, it's x squared plus 4. So even if x were some negative number and the negative portion, the x squared portion, which became positive, would be overtaken or zeroed out by the negative x, we'd still have radical 4, which would be more than enough or perfectly okay to take the natural log of. So we don't need the absolute value sign. I don't know if that explanation, if you followed all that, but if you think it through, it is not needed. Well, anyway, notice that one of our laws of logs is if we've got a product, we can take and expand and say, well, it's the log of 1/2 plus the log of the other factor, which in this case is square root of x squared plus 4 plus x. Now, the natural log of a half is some number plus our c will make for some other number, so we can combine those two and say those two constants form a new constant. We'll call it d, and the final answer could be written in this form. And in the answer key, when I check the answer, that's the way they had it. They had it with a plus c, but I made it plus d because I wanted to distinguish it from what I would say it'd be plenty fine. I'd stop right there with this problem. But I wanted you to see that it could be expressed another way. One more example. I know it's 20 minutes. We'll try to move through this last one quickly. This is the third and final situation where you might run into the form difference between two squares, but the x squared comes first. So it relates to this form. So we'll take a look at it and we'll say, geez, a in this case is 3. Our x will be 3 times the secant. Taking the derivative dx would have to be 3 sectan d theta. So I'll begin by taking out my x, replacing my x squared, taking my dx out, and boy is that ugly. Give it time. Notice that we have a common factor under the radical sign in these two terms. It is a 9. 9 is in both factors. So the square root of 9 could be brought out front, and that's where the 3 comes from, and what remains behind is the sec squared minus 1. I notice now that, geez, I can take this 3 away with that 3, and this 3 I can jump to the front. So there's 3 way out front. Under the radical sign sec squared minus 1, you may recall your Pythagorean identities that that's the same thing as tangent squared. So consider what I have now. I have the square root of tangent squared over a secant. The secant, tan, and d theta, they all remain. But now in the next step I'm thinking about, well, geez, those secants go away. And the square root of my tangent squared is a tangent. I still have another tangent down here, right? And my d theta. So I have equal to 3 tan squared theta. And for purposes of taking an integral, it's going to be to our advantage to write tan squared as sec squared minus 1 using those Pythagorean identities, because we can easily take the antiderivative of sec squared, it's just tangent, and the antiderivative of the minus 1 will be a theta. And now we'll get this answer in theta, namely 3 tan theta minus 3 theta plus c. But of course our original problem wasn't in theta. Our original problem was in x. So we're going to take that substitution that we did early on where we said, geez, let x equal 3 sec theta, and we'll say, well, that suggests that x over 3 is secant. Taking the reciprocal, wouldn't cosine be 3 over x? At least that's the way I think about secant. It's the reciprocal of cosine. So I go to my little generic right triangle and I put a theta on the lower left, and I say, well, if cosine is opposite over hypotenuse, that must mean the 3 and x are in those positions, and then I solve for that altitude, and wouldn't it have to be the by Pythagoras x squared minus 9 under a radical sign? Think about that if you need to, but it has to be that, because this side squared plus this side squared would then equal the x squared. Anyway, thinking back about the problem we just solved, this one, I've recapped it here. 3 times the tangent, going to our little diagram, tangent would be opposite over adjacent, so that's where I come up with the radical x squared minus 9 over the 3. And then I've got minus 3 theta. Now there are various ways you can say theta, but perhaps the easiest I've got here on the lower right, based on what we said earlier, that theta is the inverse secant of x over 3. You certainly could say theta is the inverse cosine of 3 over x if you prefer that. But anyway, we're going to use that now and say theta, because we want theta out. So theta, another way of saying theta, is inverse secant of x over 3. And you know, I might finally take those 3's away and state my final answer is radical x squared minus 9 minus 3 inverse secant of x over 3 plus c. So that's 26 minutes. That's more than enough on trig substitution. Good luck.